When you think about it, what is the real difference between the light from a lamp and the light from a laser? They both light things up, sure, but one is just a chaotic jumble, and the other is this pillar of absolute perfect order. Well, today we're going to dive deep into that difference. We're going on a journey to uncover the hidden rules that govern light, and it's a concept that lets us do everything from measuring distant stars to literally seeing inside our own bodies. So, let's get into it.
And here it is, plain as day. On the left, that's your standard light bulb. The waves are a total mess, right? They're all jumbled up, different colors, shooting off in every direction. It is pure chaos. But then you look to the right. That's a laser. Every single wave is marching in perfect lockstep. Same color, same direction, same rhythm. This beautiful, disciplined order, well, that's the key to everything we're about to talk about.
Now, of course, physicists have a word for this order. They call it coherence. And it's not just a vague idea of being neat. No, it's a precise measurement of how well a wave's wiggles, its peaks and troughs, line up with each other, both in space and over time. You can almost think of it as the wave's memory. How well does it remember what it was doing a split second ago, or even just a millimeter to the side? This one idea, it was about to spark a revolution.
To find the first major clue in this story, we have to travel all the way back to the early 1800s. Now, back then, most scientists, following Sir Isaac Newton no less, were convinced that light was just a stream of tiny particles, kind of like little bullets of light. But a ridiculously simple experiment, using nothing more than a few slits in a card, was about to blow that entire theory right out of the water.
So here's the setup. It's from this brilliant polymath named Thomas Young back in 1803, and it's so simple it's genius. First, he takes regular sunlight and shines it through a single tiny pinhole. Now this is a crucial step. It starts to create a little bit of order. Then that little beam of light hits a second card, this one with two narrow slits right next to each other. And finally, he just looks at what pattern shows up on a screen behind it all.
Okay, so let's just think about this for a second. If light really is just a spray of tiny particles, like sand being shot through those slits, what would you expect to see on the screen? Well, two bright lines, right? One for each slit. It's just common sense. But, as it turns out, common sense was about to get a major shock.
This is what he saw. Not two lines, not even close. He saw this series of alternating bright and dark stripes, a pattern. And Young had this incredible insight: this could only happen if light was behaving like a wave. The bright spots were where the crests from both waves added up. And the dark spots? That's where a crest from one wave met a trough from the other and they just canceled each other out. This was the smoking gun.
And Young himself said it best. He said that light waves pass right through each other, just like ripples on a pond. It's such a simple, beautiful analogy, but it completely upended our understanding of light. He had just discovered interference, the absolute definitive proof of light's wave nature, and really, the first great discovery born from the idea of coherence.
So Young proved that light could be orderly. But just seeing it wasn't enough for the next generation of scientists. They wanted to measure it. They needed to put some real numbers to this idea of order. And this shift from just observing coherence to precisely quantifying it was about to unlock some truly mind-boggling new abilities.
So scientists figured out they needed to measure this order along two main directions. First, you've got spatial coherence. That's basically asking how in sync is the wave side to side. And then you have temporal coherence, which is asking how predictable is the wave front to back as it's traveling along. Let's take a look at what that actually means.
This here is perfect spatial coherence. Imagine you could just slice a laser beam in half and look at the cross-section. Every single point across that beam is rising and falling in perfect, beautiful unison. This right here is why Thomas Young's two slits could talk to each other in the first place. They were being hit by a wave that was perfectly ordered across space.
And this is temporal coherence. The best analogy is a pure musical note that just never, ever wavers. The wave train is incredibly long, unbroken, and predictable. If you know where a peak is right now, you can predict with total certainty where a peak is going to be millions and millions of wavelengths down the road. It's really a measure of the light's purity of color.
Now here's where it gets really cool. All this stuff about quantifying order wasn't just some abstract academic exercise. It handed humanity a brand new kind of ruler, a ruler long enough to measure the stars themselves.
And just look at how fast the progress was. In 1865, a guy named Verdet figured out that even though the sun's light is chaotic because it's so far away, by the time it gets to us, it has a tiny patch of spatial coherence, but it's only 0.05 millimeters wide. Then, the legendary Albert Michelson came up with a practical way to measure temporal coherence, and it all leads up to 1920, when he and Francis Pease turned this whole idea on its head. By measuring the spatial coherence of starlight, they were able to calculate the actual physical diameter of the distant star Betelgeuse, for the first time ever. Just incredible.
So for decades, this classical, wave-based picture of coherence felt pretty complete. It all made sense. But then, in the 1950s, a bizarre new experiment uncovered a deeper, much weirder layer of order hiding right under our noses. One that would drag the whole field kicking and screaming into the strange world of quantum mechanics. See, instead of looking at the big waves, two astronomers, Hanbury Brown and Twiss, decided to look at the individual particles of light, the photons, and just count them as they arrived. And they found something that seemed completely impossible. Photons coming from a chaotic source, like a star, didn't arrive randomly. They actually tended to clump together, or bunch. So detecting one photon meant you were just a little bit more likely to detect another one right away. This discovery gave us a brand new kind of measurement called second-order coherence, which is like a secret fingerprint for light. And check out this table. For thermal light, like from a star, the value is 2, which confirms that photon bunching is real. But a laser, its value is exactly 1. Its photons arrive perfectly randomly, like raindrops in a steady shower. And then things get really strange. For some exotic types of quantum light, the value is less than 1. The photons actually avoid each other, a phenomenon called anti-bunching that simply has no explanation in classical physics. All right, so we've gone on quite a journey, from ripples in a pond all the way to bizarre quantum statistics. But the big question is, how does this incredibly deep understanding of light's order and its disorder actually change our lives? Well, the applications are frankly nothing short of miraculous.
And here is the beautiful paradox, the big twist in our story. We've learned to master both ends of the spectrum. The perfect, pristine order of high coherence lets us do things like record entire three-dimensional scenes. But just as powerfully, the complete and total disorder of low coherence lets us see inside the human body with microscopic precision.
Take a technology called OCT, optical coherence tomography. It ingeniously uses light with very low temporal coherence, a really short, messy wave. It splits this light, sends one beam into, say, your eye, and the other to a mirror. Now, because the light is so messy, interference can only happen when the light bouncing back from a very specific layer inside your eye has traveled the exact same distance as the light from the mirror. So by moving that mirror, doctors can scan layer by layer, building this incredibly detailed 3D map of your retina. It's basically an optical biopsy, no cutting required.
And then, on the complete other end of the spectrum, you've got holography. This absolutely requires perfect order. To capture a real 3D object, you can't just record its brightness. You have to record the phase of the light waves too. The only way to do that is to interfere the light bouncing off the object with a perfectly stable, highly coherent reference beam from a laser. This creates this insanely complex, microscopic interference pattern on a piece of film, a kind of map that when you light it up again, magically reconstructs the original 3D wavefront in thin air.
So, there you have it. From a simple experiment with 2 slits to a tool that can measure the stars. From a chaotic light bulb to a medical device that can save our eyesight. Our journey to understand the order within light has given us some truly incredible powers. It really makes you wonder, doesn't it? We've learned to master its classical order to see across the cosmos and deep inside ourselves. So what happens when we finally master its quantum weirdness too?